Hey everybody, it's Wednesday, November 18th, and as you can see here in the aim today, the focus for this video is really going to be to get into using friction concepts for problem solving. And so yesterday we went through a whole bunch of stuff related to friction and how it specifically ties into the inclined plane. And we're going to wrap a little bit of that up today. And then we're really going to take a good look at how friction is used in a wide variety of problems, some of which deal with inclined planes, some of which do not. Now we are getting to the point where we are really getting pretty close to synthesizing everything that we've said so far about forces and Newton's laws. And so you can expect in the next couple days a bunch of problem solving videos, a bunch of attachments to the Google Classroom posts with worksheets with problems for us to practice. And so if you have not gotten a chance to watch any of the previous videos, like the one on the Atwood's machine or the one on making free body diagrams in general, I highly suggest you do that as soon as possible, because those are going to start to figure in heavily into what we're doing. Now, to start us off for today, I want to take a look at one problem which is really similar to the stuff we were doing yesterday, but I decided not to include it in yesterday's video just because it was getting a little long. But it really kind of ties in everything that we did yesterday into like one nice, neat little problem. And so let's take a look at this problem here. This problem is in one of the old versions of the packet. Because it's in one of the older versions of the packet, I decided not to put the page number in the packet, because honestly, I forget if it is still in the packet or not. I think they might have changed it or changed the angle on the ramp in the newer version of the textbook. But anyway, you'll see plenty of similar problems to this on homeworks in the future. It says a hockey puck is sliding down an inclined plane with an angle of 15 degrees, as shown in figure P4.49. That's that figure here. You can't see the label, but that's the figure number. It says if the puck is moving with a constant speed, then what is the coefficient of kinetic friction between the puck and the plane? Now, based on everything we said yesterday, I hope you're all realizing that like one thing to definitely notice and pay attention to about this problem is that there's not a lot of information given. And they love to do this. And by they, I mean like textbooks, the AP test, anything. They love to do this kind of stuff where they give you a situation, but they don't tell you that much information about it. Because once you combine all of the equations, when you get to the end, you're going to see a lot of cancellations. And so it's really critically important for everybody to get into the mindset here that you want to work the equations with the symbols for a long time, because eventually you are going to get it to a point where you're going to see all sorts of variables start to cancel. And so here we got a puck moving with a constant speed. So they tell us that it's moving at a constant speed, and they tell us that the coefficient of friction is what we're looking for, and they give us the angle, and that's it. And so clearly, well, I hope it's clear to you by now, clearly the first thing we should be doing is we should be drawing the free body diagram. And so that's what we're going to start with. I'm going to sort of lead you through this whole thing because this is sort of like a problem that we're going to solve, but also a thing that I got to teach you / show you. And then the rest of the video will be problems that you're going to take on your own. And so for this one, obviously, the first thing we're going to do is we're going to draw the free body diagram. And so the first thing I'm going to include in my free body diagram is the weight. And I actually want to pay close attention here to drawing the free body diagram to scale. Now, it doesn't actually matter for the question because there's not like a portion of it where they ask you to draw the free body diagram for a grade. But I just want to make sure we're emphasizing this here. The first thing I'm going to show with a vector going straight down towards the center of the Earth is the weight of the block. The weight of the block always goes straight down because the weight of an object always points to the center of the Earth. The next thing we want to show is the normal force. And if we did not emphasize this enough yesterday, then we should emphasize that the normal force, because the object is not being lifted off of the plane or falling through the ramp, the normal force is always going to be balanced out by FGY, the vertical component of the weight. And so because the normal force is only equal to one component of the weight, the normal force is going to be less than the weight. And so because the normal force is going to be less than the full weight, we want to show that with a smaller arrow than we're showing for the weight. And lastly, we're going to put that force of friction in there. The force of friction should be parallel to the ramp. And you're not really supposed to make an arrow not go beyond the box, but I'm going to do that here just because the force of friction is supposed to be smaller than the normal force, because the equation for the force of friction is the coefficient of friction times the normal force. And since the coefficient of friction is a number which is generally smaller than 1, if you're taking a number that's smaller than 1 and multiplying it by the normal force, then you should obviously get a number for the force of friction that is smaller than the normal force. And just to finish this up here, because the object is sliding down the ramp, this force of friction is definitely kinetic friction. And so we'll label it with the appropriate subscript K. As we did yesterday, and you don't really need to do this if you're getting comfortable with it, but I think as definitely as we start here, it should be noted that it is helpful, because these components don't really line up perfectly, that it is helpful to do a little component diagram. And so we'll do that. I've got the normal force coming straight up. That's not that big. I got the weight coming straight down, and that's bigger than the normal force. And now this is extremely exaggerated, but the component diagrams are really like not official diagrams at all. You're actually really not supposed to include components on free body diagrams. And so I'm just going to put this not really to scale. And then I'm going to have my, basically I'm keeping the same orientation as this diagram above. I'm just kind of tilting it back down 15 degrees. So we'll have the force of friction coming up like this. This, of course, is not the weight. It's FGY because I've tilted my surface. And then this is FGX. And really now these things are supposed to be dotted for components, but it's actually really hard to do a dotted line with this, stylus pen on the computer. And so we'll leave it at that. And so it should be noted for everybody at least, and this, because this is really wacky the way that this is drawn. I know I said I'm not doing this to scale, but since this is just FGY, this really is exactly equal to the normal force. And so I'm not going to take out a centimeter ruler and check anybody's diagram or anything, but it should be shown as being like more, equal to the normal force. And of course, because this thing is traveling at a constant speed, you should recognize actually as well that the FGX is going to be equal to the force of friction. And so even though this is not to scale, just so we're all being totally clear about this, I want to take this and make it the same length as the force of friction. Okay, so let's just go ahead and run through. I'm just going to keep these down here because they're kind of out of the way. The knowns in this problem is not much. We got the angle is 15 degrees. Of course, we know G is 9.8 meters per second squared. And they told us that the acceleration, well, they didn't tell us, but we have to interpret that. Since they told us that this thing is moving at a constant speed, the acceleration here is equal to 0. And so I'm going to put AX is equal to AY, and I'm going to label that as 0 meters per second squared. Now, your first move after you draw the free body diagram is to write the equations from the free body diagram. And so that's what we're going to do here first. And so I will start, as I mentioned yesterday, I hope I was being very clear about this. It always makes sense when you're doing these friction problems to start with the sum of the forces in the y direction. And because we know the acceleration in the y direction is 0, and of course we're doing this to solve for the coefficient of kinetic friction, because we know the acceleration in the y direction is 0, we know that the sum of the forces in the y direction is going to equal 0. And so we have the upward force, the normal force, minus the downward force, FGY, is equal to 0. And we can go ahead and solve this for the normal force by moving FGY to the other side. And since we know that FGY is going to be mg cosine theta, because remember the sine and cosine switch on an inclined plane in terms of the equations for the components, all you can really do with the y equation for an inclined plane is solve it for the normal force and move on. The normal force is equal to mg cosine theta. You need that result to plug into the equation that you get for the x direction because the force of friction is based on the normal force. And so in the x direction here, we also have a pretty simple arrangement for the equation. We have the sum of the forces in the x directions equal to 0. And so we have the force going in the direction of motion, Fgx, minus the force going opposite the direction of motion, the force of kinetic friction, and that's equal to 0. And so we can rearrange that and solve it for Fgx, and we can say Fgx is equal to the force of kinetic friction. And now we can do some substitutions here. I'm going to substitute mg sine theta for my Fgx, and I'm going to substitute the coefficient of kinetic friction times the normal force for my force of friction. And since I'm running out of room, I'm going to go ahead and put that in a box. That is true in general here. And now that I have this result from my x direction equation, and the result from my y direction equation is an equation for the normal force, I can now combine these equations and go ahead and solve for what I need to solve for. And so the first thing I'm going to do over here is I'm just going to list these equations. And so when I'm listing these equations here, I've got Fn, the normal force, is equal to mg cosine theta, and I have Fgx, which is mg sine theta, is equal to the coefficient times the normal force. And so your first move with the math here is to take your equation, mg sine theta equals the coefficient times the normal force, and you sub in your equation for the normal force. So I have mg sine theta equals the coefficient of kinetic friction times mg cosine theta. And so notice here, because I have an m and a g on both sides of the equation, they cancel. And that leaves me with just sine theta equals the coefficient of kinetic friction times cosine theta. And hopefully now, based on what we did yesterday, you see where this is going and it makes sense to you here. When I solve this for the coefficient of kinetic friction, I get that the coefficient of kinetic friction is equal to sine theta over cosine theta. And that means the coefficient of kinetic friction is equal to the tangent of the angle. Now, as I mentioned before, I just want to take a second to talk about this. As I mentioned before, I said this was kind of like a problem that we're solving, but also is a thing that I'm supposed to be teaching you as well. When an object is moving at a constant speed on an inclined plane, the coefficient of friction is equal to the tangent of that angle. Now that probably looks familiar to you because what we also said is that the coefficient of static friction is equal to the angle that this thing is tilted to that causes the thing to start to move. And so we see this similarity in those two results. Now, there's an extremely good reason why we see those two results for those two particular situations, and we'll address that here once we wrap this up. But this is a very important thing to realize. When an object is moving at a constant speed, the coefficient of kinetic friction is equal to the tangent of the angle. And so to finish this up here, because the question actually asked us not to just derive the equation, but to solve for it, we can say the coefficient of kinetic friction is equal to the tangent of the angle here, which is 15 degrees. And when we plug that into our calculators, we should get the coefficient of kinetic friction is 0.2679. And so we can call that 0.268 or 0.27. It doesn't really matter. And that's it. all we need to solve for the coefficient of kinetic friction is the angle. We don't need the mass. We don't need to know the type of material. All we need to know is the angle the ramp needs to be lifted to in order to cause this thing to move at a constant speed. Pretty cool. Now, of course, we have a pretty good question to answer here. And that question is, why is the equation for the static coefficient when the object is at rest, that the static coefficient is equal to the tangent of the angle, the same as the equation for the kinetic coefficient when the object is moving with a constant speed? Take a second to pause this video here and think about that. When you hit play, we'll go over the answer. So the question here is, why is the equation for the static coefficient when the object is at rest the same as the equation for the kinetic coefficient when the object is moving with a constant speed? And the answer here, I think, makes a heck of a lot of sense. In both cases, the object has no acceleration. Whether it's at rest or moving with a constant speed, there's no acceleration, which means there's no net force. And so from a forces perspective, the situations are identical. And that's a crucial point here. The normal force is canceled out by the FGY, and the FGX is canceled out by the force of friction. There's no net force in either direction. This is super, super important. Take a second to pause this video here and write that down. You don't have to write down the question, but you should write down the general point here, which is that these situations are identical from a forces perspective. And when you hit play, we'll go ahead and take a look at another problem. Okay, so now I want to take a look at one last problem to really fully wrap us up for just the inclined plane stuff before we move to a general mix of friction problems. And so this problem also is just a multiple choice here that I'm going to show on the screen. This is in the packet, I think. It may be in an older version, though, so I don't have the page number here, but don't worry about it. It says a skateboarder rolls down a rough hill with an increasing speed. Which of the following free body diagrams describes the skateboarder? I'd like you to take a minute to pause this video here and think about two things. First, I'd like you to think about what the right answer is, and then I'd like you to think about why the right answer is what it is. So I'd like you to take, let's say, 2 minutes to pause this video here, think about what the answer and an explanation would be, and when you hit play, we'll go over it. Okay, so you're going to see a bunch of questions like this, these multiple choice questions asking you about a correct free body diagram. And the key thing that everybody needs to realize is that the free body diagrams that they show you in this question, in all these answer choices here, are correct based on two things, if it's the right answer. It has to show the forces going in the right direction, and it has to show the forces drawn to the right scale. And so looking at all the answer choices here, I think the first and smartest thing to do here is to cross out answer choices that are immediately wrong. And the first one that I'm seeing that's immediately wrong is choice B. And the reason why choice B is wrong is because it says the force due to the velocity. And force due to velocity is not a thing. As we know, objects move down an inclined plane because of the component of their weight that is directed down the incline. That's an important thing to realize. Okay, so looking on, we can see here that C is definitely wrong because it shows the normal force being exactly opposite of the weight when it's not. Only the Y component of the weight is opposite the normal force, and that also means D is wrong. And as it turns out, both A and E are showing you the forces in the appropriate directions. Notice here, based on the way this is shown, and I'm going to try to do this in red here, that means the ramp is tilted like this in these diagrams. And so now the question is, well, which one is showing you these forces drawn to the appropriate scale? And if you look, E is wrong. E is wrong for a bunch of reasons. First of all, the weight is supposed to be the largest force shown there, and the friction is shown as being the largest force. It also shows the normal force as being equal to the weight, but that's not true. The normal force is actually supposed to be less than the weight because the normal force is only equal to FGY. And the friction force is supposed to be smaller than the normal force because the coefficient of friction is a number that's usually smaller than 1. And when you take a number smaller than 1 times the normal force, you get a smaller number. And that makes the answer A. And so what I wrote here is a decent explanation, is the answer is choice A. The weight, which is the largest force, acts straight down because the force of gravity acts toward the center of the Earth. The normal force, which is the next largest force, acts perpendicular to the surface, which notice actually also is perpendicular to the friction force. The normal force is smaller than the weight because the normal force is only being balanced out by the vertical component of the weight, FGY. So it must be smaller than the weight. The force of friction, the smallest force, acts parallel to the surface and acts in the opposite direction of FGX, which is the force pulling the object down the ramp. Right? So the kinetic friction force is always going to act in the opposite direction of motion. In this case, it's opposite of FGX because FGX is what's pulling the object down the ramp. The friction force is smaller than the normal force because the coefficient of friction is a number which is almost always smaller than 1, and the friction force is calculated by multiplying the coefficient of friction by the normal force. Now, you are definitely guaranteed on our dynamics test to have to explain why a free body diagram looks the way it does. And you will probably be asked to explain why this free body diagram looks the way it does. So if I were you, I would take a second to pause this video here and write that down. And when you hit play, we'll move on to some more general friction questions. Okay. So the next question I want to look at is a question that actually did appear on a practice test for an AP Physics 1 exam a bunch of years ago. And so this really is a representative question for what you could expect to see on the AP test. Now, I think as you all have realized, sometimes they give you questions on the AP test which are a little crazy. As you probably noticed on the graphing motion test, some of those multiple choice are hard. And so you want to try to help yourself as much as possible by sort of boiling the thing down to basics. And so let's take a look at the question and sort of make an attempt to simplify it. So it says here, the figure above shows the forces exerted on a block that is sliding on a horizontal surface. The gravitational force of 40 newtons, the 40 Newton normal force exerted by the surface, and a frictional force exerted to the left. The coefficient of friction between the block and the surface is 0.20. Then the question says here, the acceleration of the block is most nearly. To start us off, I'd like you to pause this video here and just take a second to analyze the diagram. I want you to think here about the situation. What does the situation look like? Where's the surface? What's actually happening to the object, etc., etc. And when you hit play, we'll go over it. All right, so this question, the reason why I asked you to consider what this situation might look like here is because this question usually reveals a pretty big misconception about friction. And so it's important to realize here that based on the way the weight and the normal force are shown, the surface has got to be oriented like that, right? Because the normal force, which they tell us is 40 newtons, and is also exactly equal to the weight, which is 40 newtons, they tell us here that the normal force is equal to the weight, and the normal force is always perpendicular to the surface. And so the idea is this has got to be a flat horizontal surface based on all those facts. And usually what I notice is that a lot of people, when they answer this question, say, well, the acceleration of the object has got to be to the right because that's the way the object is moving. Now, how do we know the object is moving to the right? Well, it tells us here that the block is sliding on the surface. And because the block is sliding on the surface, that means this force here is a force of kinetic friction. And the force of kinetic friction always acts opposite the direction of motion. So we do know for a fact that this object here is moving to the right. But there is no force acting to the right. The only force horizontally acts to the left. And so that means here that the acceleration has to be to the left, even though the object is moving to the right. Now, what exactly does that mean for the motion of the object is a perfectly reasonable question to ask. And I think you gotta sort of try your best to picture this stuff here as best you can. And we're going to try to use a simulator for this. And so because this object is moving to the right, I'm going to set the initial velocity as 5 and make it positive. And so this thing is going to be moving to the right. I'm also going to make these vector lengths a little shorter just so we can see them. Or I'll zoom out here. We could do that too. And so we have the weight acting straight down. We have the normal force acting straight up. And we have the force of friction. Notice our coefficient of friction is 0.2 here. We have the force of friction acting to the left. And now I can make these vectors a little longer so we can at least see the force of friction. Essentially what's happening here is this object is slowing down to a stop. If you take something and you just give it one good initial push, like I'm holding a mouse here in my hand, if I just take this thing and throw it, you might be able to hear the noise. It eventually comes to a stop because of the force of friction. And the second I let it go, there's no longer an applied force, and so the thing just slows down to a stop. And that's basically all that's happening here. The object is given one good throw, and it slows down to a stop. That's it. And so to look at it again, now I've changed the initial velocity to 10, so it'll go a little faster, at least in the beginning. It's given one good push, but because the net horizontal force is to the left, the object is simply slowing down to a stop. The force of friction, notice, is reducing the velocity. It's getting smaller and smaller and smaller and smaller. It's traveling less and less and less and less distance as time goes by, and eventually the object comes to a stop. And so the question here is about the acceleration. And so what I'd like you to do here, now that we've recognized that the object is in fact just slowing down to a stop because a free body diagram shows you all the forces acting on the object. That's it. That's what it shows. And so there is no applied force here because if there was, it would be shown. Now that we know all the forces, we understand the situation, I'd like you to go ahead and solve for the acceleration. But first, I want you to go ahead and write this down. It says here, note, while it is sometimes true that the force of friction causes objects to move, that's really only true for static friction. When an object is sliding and the kinetic friction force is acting on the object, it always acts in the opposite direction of the motion. And that's true. I actually want to add something onto this, and that's true whether or not there's an applied force. And so the important thing to realize here is that the free body diagram shows all of the forces. And since there is no applied force in the diagram, there is no applied force acting on the object. I want you to go ahead and pause this video and do two things. The first thing I want you to do is I want you to write that down. And the second thing I want you to do is use the information given in the problem to go ahead and solve for the acceleration. And when you hit play, we'll go over the solution. Okay, so they tell us in this problem here that the normal force is equal to 40 newtons. They tell us the weight is equal to 40 newtons. They tell us the coefficient of friction is 0.20. And so the first thing we're going to do when we solve this problem is we're just going to go ahead and write down the list of knowns here. So we're told that the normal force, Fn, is 40 newtons. we're told that the weight, Fg, is 40 newtons. Of course, we should know that the acceleration due to gravity is going to be used here. And so we have g is 9.8 meters per second squared. And we have the coefficient of kinetic friction as 0.2. And we're looking for the acceleration a. And so I think it makes pretty good sense here because you should know we're going to need it. We should go ahead and solve for the mass, right? Because F net is equal to ma. And so because the F net is equal to ma here, we need the mass. And so we're going to use the equation Fg equals mg. And if we solve that for the mass, we get the mass is equal to Fg over g. And so when we plug in those numbers here, I'll just do that over here, we get the weight, 40 newtons, over 9.8 meters per second squared. And when you do that math, 40 divided by 9.8, you get 4.08 kilograms, which is approximately equal to 4.1 kilograms. And so there's our mass. Now, the problem already had a free body diagram, but just to remind you, it looked a little something like this. And then with the friction force coming over here. And so what you should notice here from the free body diagram, which is what we need to calculate this thing now, we would take ma and set it equal to all the forces in the direction of motion minus all of the forces opposite the direction of motion. And so we have 0, because there's nothing in the direction of motion, minus the force of friction. Now, whether you do this like that or not, it doesn't really matter. What we usually say is take all of the forces in the direction of the acceleration minus all the forces going in the opposite direction. And so because we usually have the free body diagram take care of the signs for us, we're just going to say, let's stick with that rule. And the mass times the acceleration is equal to all the forces in the direction of the acceleration, the force of friction, and then that's it. And so we can sort of expand this out by saying ma is equal to the coefficient of kinetic friction times the normal force. And so that means the acceleration here is just going to be mu times the normal force over the mass. And so plugging in our numbers here, we have 0.2 times the normal force of 40 newtons over the mass here, which is 4.1 kilograms. And so when we take 40 times 0.2, that gives us 8. And then when we divide that by 4.1 kilograms, we have 1.95 meters per second squared, which is approximately equal to 2 meters per second squared. Now, of course, here, getting 1.95 is not really an issue, even though the answers say 2 meters per second squared. It's not necessarily a significant figures issue. On the multiple choice section of the AP test, it says for convenience, you can use the approximate value of g as 10 meters per second squared. And so that's another little tip or trick, because remember, you have 100 seconds to answer these multiple choice questions. You can quickly in your head or in your calculator do 0.2 times 40. And that's the friction force, 8 newtons, and then divide that by the mass. And you could say, well, what's the mass? It's just going to be 40 over 10, which is 4. And of course, 8 over 4 is 2. But that's it. That's the point here. Solving for the acceleration here requires you to recognize that the only force acting on the object is the force of friction. And so let's just write one more note about that before we go or move on from this problem. And this note here says when an object is sliding to a stop because the applied force stopped acting on it, the only horizontal force acting on it is the force of friction. Since a free body diagram shows all of the forces acting on an object, there is no applied force acting on the object in this problem, so the object is accelerating to the left, because that's the direction of the force of friction, even though the object is moving to the right, which we can tell because the force of friction is opposite the direction of the motion. That's a very important thing for everybody to recognize here. So take a second to pause this video here and write that down. And when you hit play, we'll move on to the problems on the worksheet that were attached to the post for today. All right, so if you go to the post for today, you will see a worksheet. The title of that worksheet should be like AP Physics, Newton's Laws, Assorted Problem Solving Worksheet. And I want to take a look at all of the questions on that sheet because they're all, in my opinion, real good questions. And we're going to do them in order. If you go to that sheet, the first problem looks like this. And this one is B3 WWT 66. It says 2 blocks at rest, normal force. And it says 2 blocks are identical and both are at rest. A student comparing the normal force exerted on the block by the surface in the two cases states, since both blocks are identical, I think the normal forces are the same because in each case, the normal force will be equal to the weight. The question is asking what, if anything, is wrong with this contention. If something is wrong, identify it and explain how to correct it. And if the contention is correct, explain why. You should know everything that is required to answer this question. So I'd like you to take a minute to pause this video here, answer the question, write not only the answer, but also the explanation. And when you hit play, we'll go over it. Okay, so the key difference between these two situations, even though the blocks are identical and even though the blocks are both at rest, is that in the first instance on the left, the object is sitting on a flat horizontal surface, and in the second case, the object is on an inclined plane. So the difference here is pretty simple. In case one, the one on the left, the normal force is being countered by the full weight of the object because those forces are equal and opposite because the object is at rest. Whereas in the second case, case 2, the normal force is only being countered by a component of the weight, which is smaller than the actual weight. And so the full answer here is pretty straightforward. Even though the blocks are identical, the normal force always cancels out forces acting in the opposite direction. Since those forces are different in these situations, the normal force is not the same in each case. And that's it. That one's pretty straightforward. It's a good thing to know nonetheless. When an object is on a flat horizontal surface, the normal force is equal to the weight. But when an object is on an inclined surface, the normal force is only equal to the component of the weight which is acting in the opposite direction of the normal force. Take a second to pause this video and either write this down or amend your explanation, whatever might have been missing from your explanation. And when you hit play, we'll move on to the next one. Okay, so let's move on to the next one. The next problem here, number 2 on this worksheet, is a really good problem. It says here in this question, B3 CT35, blocks moving at a constant speed, force on block. It says a block is moving to the right across a rough table at a constant speed of 2 meters per second. The tables and the blocks are identical in the two cases. In case A, the block is pushed with a stick, and in case B, the block is pulled with a string. The angle the applied force makes with the horizontal is the same in both cases. Will the magnitude of the force on the block by the stick in case A be greater than, less than, or equal to the tension on the block by the string in case B? If you missed it, because I think the wording of the question is kind of weird, they're basically asking you to compare the size of F, the applied force exerted by the stick, to the tension in the string. I think it is a super helpful thing here in order to answer this question to draw a free body diagram. And that's all I'll say. I'd like you to take a minute to pause this video here and draw the free body diagrams and try to use the evidence from the free body diagram to answer the question and construct an argument. And when you hit play, we'll go over it. Okay, so as I mentioned here, drawing the free body diagram is going to be crucial. And I'm going to draw two free body diagrams here because I have two situations, case A and case B. Just remember, as I flip to the next slide, of course, you might have this in front of you now. The first case, case A, is the one where the force is going down, and case B is where the string is going up. And so there's an upward tension force here. And so I'm going to label this as case A, case B. And so in both of these cases, for sure, I have a weight going down, right? And so I'll add that for both of them. The difference here, a major difference, is that in case A, where this force is coming down, I'm going to have this force coming down like this at an angle. And I'm not going to go too nuts about the angle or the scale here, because we'll have to do that kind of thinking later. Whereas in case B, I have the tension force coming up. And that really is going to make all the difference, if you haven't realized already, is the direction of the tension force. In both of these cases, I have a normal force coming up. And looking at the diagram here, of course, because it says that these blocks are moving at a constant speed, there has to be a force of friction. Because if there was an applied force in the x direction, there would have to be a force of friction to cancel it out to make the thing move at a constant speed. And so I've got a force of friction acting to the left in both cases. Now, I'm going to violate my usual rule here. And my usual rule is that we do the y component first because I want to make a point. And so it's important to realize for the x direction equation, we have a very important truth revealed to us that this thing is moving at a constant speed because the sum of the forces is going to be 0. And so what that means for case A is that the x component of the applied force, which acts along here, right? That's not supposed to be in the official free body diagram, but I'll just draw it for now. The x component of that applied force, F, is going to be equal to the force of friction. Whereas for this one, the x component of the tension force here is going to be equal to the force of friction. And so I'll have Ftx is equal to the force of kinetic friction. And so now notice if we expand this out here on the left side on case A, I'm going to have F times the cosine of the angle. Remember, the sine and the cosine go back to their ordinary order here, where the x goes with the cosine and the y goes with the sine, because this is not on a ramp anymore. The angle that we're dealing with is an angle from the horizontal. And so I have F cosine theta equals the coefficient times the normal force. And over here, I'm going to have Ft cosine theta equals the coefficient times the normal force. And what you should realize when we solve this for F over here and Ft over there is that my equation for F is going to be the coefficient times the normal force over the cosine of the angle. And for my Ft, I'm going to have the coefficient times the normal force over the angle. And I hope everybody realizes here what this whole problem hinges on now. This whole problem hinges on the fact that in case A, the magnitude of the force applied by the stick, that F, is directly proportional to the normal force. And that's what matters here. Why is that what matters? Well, it's because the coefficient of friction is the same. It's the same box, and it's the same surface. The table and the blocks are identical in the two cases, is what the problem says here. And so the coefficient of friction here in both of these situations is going to be the same. And so because the coefficient is the same and the angle is the same, because it says that in the problem also that these angles theta are the same, then that means the main difference in what we're going to see for the applied force is the normal force acting on the blocks. And here's the point. The point here is that since the force is going up in case B, but it's going down in case A, tells us that we're going to have different normal forces. In other words, the vertical component of the applied force is either pushing the block into the surface or raising it up from the surface. And so that means we're going to have a different normal force. And so in the y direction here, it should be clear to everybody that it does not say anything about this thing being lifted up from the surface. And so that means in both cases, the sum of the forces is going to be equal to 0. Now we got to think long and hard. Because the sum of the forces are going to be equal to 0, we're going to have all the upward forces added together minus all the downward forces are equal to 0. And so in case A, my upward forces are the normal force, and that's it. And my downward forces are Fg and Fy, the vertical component of this applied force, goes down. And this should make sense here that the normal force is equal to Fg plus Fy. In other words, that the normal force is going to be bigger than the weight because that vertical component of this applied force F is going down and pushing the block into the surface. And according to Newton's third law, if the block is pushing into the surface more, then the surface is pushing up on the block more, thus increasing the normal force. By contrast, in case B, we have the upward forces, the normal force, and the vertical component of the tension, Fty, minus the downward forces, which is just Fg, is equal to 0. And so that means the normal force is, I got to add Fg over, so I'll have Fg, and then I got to subtract over Fty. And so that means the normal force is the weight minus the vertical component of the tension. And so here, in a rather straightforward way, we can see the true difference. According to the x direction equation, the force is directly proportional to the normal force. That's true for both. The force is directly proportional to the normal force. And the key idea here is that the normal force is bigger in case A than it is for case B. And so because the normal force is bigger, essentially what we're saying is there's a larger force of friction that needs to be battled, so to speak, in case A than there is in case B. And since there's a larger friction force that needs to be overcome, this force has to be larger in order to combat that friction force. Now, you could go through and solve for the whole thing, but it's not totally necessary here because we can see the relationships just by looking at this. And so what we can say for the answer here is pretty straightforward. In order to keep the block moving at a constant speed, the x component of the applied force, whether that's a tension or the force from the stick, is equal to the force of friction. Since the friction force is directly proportional to the normal force, whichever situation has a larger normal force will have a larger friction force. In case A, since the y component of the applied force is pushing the block into the surface, more normal force, which is upward, is required to keep the vertical acceleration 0. Since the normal force is larger in case A, the friction is larger, which makes the applied force in the x direction larger, which is what makes F larger. And that's the idea. Now, that's a lot, But breaking it down into little pieces, I hope, makes that fairly simple to understand. The whole point is, since this thing is moving at a constant speed, we know that whatever the friction force is, that's going to be equal to the x component of the applied force. The x component of the applied force in these problems is given by the equation F times the cosine of theta. Since the angle is the same in both situations, essentially what we're seeing is that whichever one has a bigger x component of the applied force is going to have a bigger applied force because they're directly proportional and the angle is the same. And the larger force of friction, because the force of friction equation is given by the equation, the coefficient times the normal force, we can see that whichever one has the larger normal force is going to produce a larger friction force. In case A, since the block is being pushed into the surface, we see a larger normal force. The larger normal force tells us there's a larger friction force. The larger friction force tells us there's a larger x component of the applied force, and the larger x component of the applied force tells us there's a larger applied force in general. It's a lot, but the logical progression here, I hope, makes sense. And if it does not, please make sure you ask a question about it in the comments to this post. Take a second to pause this video here and write that down, and when you hit play, we'll wrap it up for today. All right, everybody. Now that is it for today. As you probably noticed, there are 2 more problems on that sheet, but because this video is getting a little long and we are actually in pretty good shape as far as the pacing of the course is concerned, we will pick back up with those 2 problems tomorrow. This video would be approaching an hour and a half if we ended up doing both of those problems, and so let's just go ahead and call it a day for today. Now, as you saw online, there's a little bit of homework due tomorrow. So I will post the solution sheet for that homework tomorrow, as well as a video which is going to have you do those other 2 problems on this sheet and some additional ones as we wrap up this friction and forces unit and get some practice doing the applications and solving the problems. All right, everybody. Have a good one.